My video on the history of oil and gas exploration in Jamaica generated a lot of interest. People seem to either love the idea of oil or absolutely hate it. Some people see nothing but dollar signs, Others are deeply concerned about issues such as oil spills, fossil fuels and their link to climate change and so on. Economists often point to the resource curse, while others worry about the geopolitical consequences that can accompany the discovery of valuable natural resources. The argument goes that if a country like Jamaica were to discover significant oil reserves, larger and more powerful nations might create obstacles that make it difficult for us to fully benefit from our own resources. Whatever your position on oil and gas, one thing is certain: everyone has an opinion. Discussions about natural resources can become surprisingly emotional, bringing out competing interests and agendas and strongly held beliefs. As a geologist, though, my primary interest is not the politics around the resources, but the science and the engineering. I'm not here to argue whether Jamaica should or shouldn't pursue oil if economically viable quantities are ever discovered. What fascinates me is the work of the geologists who have come before us and the science that governs the formation of the Earth's resources, from minerals and groundwater to oil and natural gas. While many debates focus on the politics and the economic implications of natural resources, far fewer people stop to ask some fundamental questions. How did we get these resources in the first place? How did they form? And how do we find them? And if they are ever discovered, how do we extract them after navigating all the legal and regulatory and environmental and administrative requirements required for the development of an industry? These are the questions we'll be exploring today. This video is intended for the layperson and will cover the basics of petroleum geology. To truly understand the origins of oil and gas, we need to understand some processes that take place over very long periods of geological time. Oil basically started as dead organisms that lived and died millions of years ago, which is why it is called a fossil fuel. What happens is that you have a marine environment thriving with life, particularly tiny organisms known as plankton. Think of Plankton from SpongeBob SquarePants. Well, not exactly him, but if you're familiar with the reference, you'll get the idea. In these prehistoric seas and oceans, plankton and algae flourished depending on factors such as nutrient availability and the climate at the time. Over time, countless numbers of these organisms died. As they died, they remained settled to the bottom of these ancient seas and oceans. In many cases, the bottom waters were low in oxygen, which slowed down the decomposition and prevented much of the organic material from being completely broken down or oxidized. Eventually, these organic remains were buried beneath thick layers of sediment such as mud, silt, and sand. As more and more sediment accumulated, the remains were buried deeper and deeper. So the oil that we all love or hate or love to hate started with this surprisingly simple process. But in the immortal words of the OxyClean guy from those cheesy infomercials, but wait, there's more. We're only just getting started. In the next segments, we'll look at what happens to all this buried organic material and how it eventually becomes oil and gas. So as this plankton-rich sediment gets buried deeper and deeper, both pressure and temperature begin to increase. Over time, the organic rich sediment eventually becomes what petroleum geologists call source rock. Within this source rock, a waxy organic substance known as kerogen forms. Think of kerogen as the raw material that eventually gets transformed into oil and gas. Now here's where the cooking begins. As the source rock is buried deeper underground, temperatures continue to rise. When the temperatures reach roughly 60 to 150 degrees Celsius, the kerogen begins to break down and generate crude oil. Petroleum geologists refer to this temperature range as the oil window because it is the zone where the organic matter matures into oil. If temperatures continue to increase beyond the oil window, then the kerogen and even some of the oil itself can break down further to produce natural gas. This generally occurs at temperatures of about 150 to 200 degrees Celsius, a range generally called the gas window. And that, my friends, is the one key difference between oil and gas. It really comes down to the temperature and pressure conditions under which these long dead organisms were cooked, so to speak. Without getting too technical, the term petroleum geologist used to describe this process is thermal maturation. Of course, if you're exploring for oil and gas, you need some way of figuring out whether the rocks in an area ever reach these temperatures in the first place. And that's where things get interesting. Petroleum geologists use a variety of indicators, sometimes called paleothermometers, to reconstruct the temperature history of rocks. Things like organic matter, characteristics, certain minerals, trace elements, and even isotopes can provide clues about how hot a rock became during its geological journey. But anyway, we'll leave all this geochemistry lesson for now. In the next segment, we'll look at what happens after oil and gas form, because contrary to what many people think, they usually don't stay where they were created. Now, I think it's almost common knowledge that oil floats on water. In science, they'll tell you it's because of density. Oil is less dense than water, and as such, it tends to float on top of it. Interestingly, both oil and water move through underground rock layers. And you know, I've heard it said in some quarters that hydrogeologists, those who study groundwater, often make excellent petroleum geologists, and vice versa. When you think about it, both disciplines involve studying the movement of fluids in the subsurface, and many of the same principles such as porosity and permeability and hydraulic conductivity and fluid flow come into play. All of them are applied across both disciplines. Well, let me know in the comments, do you agree with that idea that hydrogeologists make good petroleum geologists and vice versa? Do you know anyone, for my geologists out there in particular, do you know anyone who has successfully made a jump from one field to the other? Anyway, once oil and gas are generated, they begin to migrate through the subsurface. As they move, they tend to travel through rocks that are porous and permeable, rocks that contain connected spaces through which fluids can flow. Things like coarse-grained sandstones and fractured limestones are excellent examples of what petroleum geologists would call reservoir rocks. And let me tell you, this is one of the reasons petroleum geologists spend so much time studying faults and joints and fractures. Faulting can create fracture networks within rocks, particularly limestone, which can dramatically improve their ability to store and transmit fluids. Once oil and gas enter a reservoir rock, they will generally continue migrating upward because of buoyancy, unless of course something stops them. And that's where cap rock comes in. An impermeable rock layer such as shale can act as a seal, preventing the oil and gas from escaping to the surface. Over geological time, tectonic forces may fold and deform these rock layers, creating structures that can trap hydrocarbons beneath the cap rock. And this is another reason geologists spend so much time studying folds. We don't study them just to understand the tectonic history of an area. Many folds, particularly anticlines, have been proven to be excellent traps for oil and gas. So at this point, we have organic matter that has been buried, cooked, transformed into oil and gas, and then migrated into a trap. The next question now is, how do we actually find it? Now, oil exploration is a very involved process. In some cases, it can take decades to go from initial exploration to actual production. Sometimes several different companies may carry out exploration work over many years before a discovery is ever made. That said though, every petroleum system is a little different and no two exploration programs are exactly alike. What I'm about to describe is a very broad overview of the journey from exploration to discovery and ultimately production. So first, let's talk about exploration. Before investing millions of dollars into expensive equipment and drilling programs, geologists spend a lot of time studying the history and structure of rock layers to identify sedimentary basins that may contain oil and gas. This often involves field work where geologists collect rock samples, map outcrops, and investigate features such as natural oil and gas seeps within an area of interest if they exist. Remote sensing is also an important part of the process. This involves analyzing satellite imagery and aerial photographs to identify large-scale geological features such as faults and folds, which, as I mentioned earlier, can play an important role in creating traps and migration pathways for hydrocarbons. Once the geological mapping is completed, exploration is usually followed by geophysical and seismic surveys. These surveys are designed to create an image of what lies beneath the surface. On land, special trucks equipped with seismic vibrators generate vibrations that travel into the ground. As these vibrations encounter different rock layers, they reflect back toward the surface, where they are recorded and analyzed to produce images of the subsurface. Then there is offshore exploration, like the type that United Oil and Gas has conducted offshore Jamaica, which has generated a lot of discussion in the recent months. Offshore seismic surveys work in a similar way to those on land. A survey vessel releases controlled low-frequency sound waves into the water at regular intervals using what is known as an air gun. These sound waves travel through the water and they penetrate the seafloor and reflect off the different rock layers beneath the ocean floor. The returning echoes are recorded by a sensitive instrument called hydrophones, and the data are processed to create detailed two-dimensional and three-dimensional images of the subsurface. Eventually, if the geological and geophysical evidence looks promising enough, exploratory drilling begins. This is where companies drill an exploratory well to determine whether oil or gas is actually present. Of course, this cannot happen without the necessary licensing and permits and environmental reviews and the regulatory approvals and so on. And to my knowledge, oil and gas exploration is heavily regulated in most countries around the world. If exploration drilling confirms the presence of a commercially viable reservoir, additional studies are conducted to evaluate its size and economic potential. If the results are favorable, the field may eventually be developed and permanent production wells and supporting infrastructure may be installed. If the discovery is not economically viable, the well is permanently plugged and abandoned, and the site is rehabilitated according to the regulatory requirements. And that's the part that many people don't realize. Finding oil isn't as simple as drilling a hole in the ground and striking it rich. It can take years or even decades of geological studies, seismic surveys, permitting, and drilling before anyone knows whether a prospect is worth developing at all. So in the next segment now, we'll talk about how oil and gas are brought to the surface. Once a well is connected to a reservoir, the reservoir is often under high natural pressure, a result of the weight of the overlying rock and or the compressed gases trapped within the formation. Not surprisingly, this very same principle applies to most water wells that are drilled in confined aquifers, but we can talk about that in another video. In this state, the oil is pushed up the wellbore naturally. This is known as primary recovery. As pressure begins to drop over time, artificial lift methods are introduced. Pumps such as the iconic pump jacks, or what are commonly called the nodding donkeys, are installed by engineers to continue bringing oil to the surface. In scenarios where the oil is particularly viscous or where reservoir conditions are more complex, other technologies are used. And one of these is called the gas lift, a method where high pressure natural gas is injected into the production tubing, and by mixing the gas with the oil column, the overall density of the fluid is reduced, making it easier for the remaining oil in the reservoir to be pushed up to the surface. And alternatively, there's progressive cavity pumps, which use like a screw-like rotor to bring thick viscous fluids up to the surface. It's especially useful in situations where conventional pumping systems would struggle to lift the oil efficiently. Regardless of the lifting methods though, production is controlled at the surface by a structure known as the Christmas tree. And it's a critical assembly of valves and gauges that are installed at the wellhead. The system acts as the main control center for the well, regulating pressure and flow rate, while also serving as an essential safety barrier for the entire operation. It allows the operation to quickly isolate the well for maintenance or shut down during emergencies. And honestly, there's a lot more engineering happening here, much of it outside of my own area of expertise, but I think this gives a useful general picture of how production actually works once oil is brought to the surface. So let's go over the full range of processes now, from the long natural processes over geological time to the human-made or engineered steps that bring oil to the surface, where it is then refined and even still in this present day powers much of the world. So first there is the deposition of mud packed with the remains of marine organisms such as plankton and algae at the bottom of a stagnant sea. Over geological time, increasing heat and pressure transform this organic material, gradually generating oil and gas. Next comes the migration of these hydrocarbons through rock layers that are porous and permeable. This oil and gas then move upward through the subsurface until they are trapped by an impermeable layer known as a cap rock, which prevents them from escaping to the surface. Finally, humans, through a combination of geological insight and modern exploration techniques, they locate these accumulations and use advanced engineering to extract them. And that's the full journey, from microscopic organisms living in ancient seas to the energy resources that continue to power much of the world today. I hope you found this information useful. As always, thank you for watching, and I'll see you in the next one. Take care.